Welcome and thank you for joining us for today's webcast, P2P Pumped Two-Phase Cooling for High Heat Flux Applications, sponsored by Advanced Cooling Technologies and TechBriefs Media Group. I'm Billy Hurley, Associate Editor with TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you can submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible at the conclusion of the presentation, and those questions not addressed during the live event will be answered after the webcast. Also, twice during the presentation, we will present you with poll questions, and we invite you to answer those at that time. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speakers. Pete Ritt is Vice President, Technical Services for Advanced Cooling Technologies. Mr. Ritt joined ACT in 2010 to head ACT's technical services business. During his time, the group has successfully provided thermal consulting, design, and prototyping solutions to commercial customers in the lighting, renewable energy, industrial equipment, medical, and other industries. Also on the line for our Q&A part of the presentation is Dr. William Anderson. Bill Anderson is the Chief Engineer at Advanced Cooling Technologies. He has over 30 years' experience in two-phase heat transfer. Dr. Anderson has designed and developed a number of unique heat transfer devices. In addition to pumped cooling, his work includes aircraft, anti-icing, turbine engine cooling, simultaneous heat and mass transfer at cryogenic conditions, direct contact condensation, and designing components for energy conversion systems. So at this time, I'd like to hand the program over to our first speaker, Pete Ritt. Pete?
Thank you, Billy. I'm Pete Ritt, and along with Dr. Bill Anderson, we are delighted to be with you. For today's webinar, we'd like to present an emerging new thermal management technology for design engineers to consider when solving challenging high heat dissipation problems, pump two-phase cooling. We call it P2P for short. Two-phase cooling generally means using a cooling fluid where at least some of the fluid is intentionally transformed into vapor upon heating, resulting in a vapor-liquid mixture in the fluid loop. Because a fluid's latent heat of vaporization can be 2 orders of magnitude larger than the sensible heat of single-phase liquid cooling, there can be a significant improvement in heat absorption per unit volume of fluid. Pump two-phase cooling has been the focus of research in government and academia, but is seeing more broad adoption in the commercial sector because of some very attractive performance features. In this webinar, we will do an overview of the market outlook for pump two-phase systems, then discuss advantages and challenges of the technology compared to pump liquid systems. We will then review 3 applications: laser diode cooling, electronics cooling where isothermality is important, and cabinet enclosure cooling. In each of these examples, pump two-phase cooling solutions are being implemented. For each of these applications, we will highlight what feature benefits of pumped two-phase cooling make it the preferred thermal solution. We'll conclude by looking at some advances in P2P technology, microporous coatings, and demonstration of insensitivity in gravitational orientation, and then try to answer some of your questions. For the past few decades, excellent thermal management solutions have been attained by using well-established technologies such as air-cooled and pumped liquid systems. However, several emerging thermal management applications would have such large space and power requirements for either an air-cooled or pumped liquid system that they are no longer viable solutions. Some of these applications are pictured here: IGBT and power electronics, data center cooling, hybrid battery packs, and new vertical cavity surface-emitting lasers, to name a few. In some projected application, heat fluxes upwards of 1,000 watts per centimeter squared are predicted. Therefore, there is an increasing need for a compact, high heat flux thermal management system. Pump two-phase cooling offers a potential solution to address that need. Let's review some of the basic principles of pump two-phase cooling. P2P uses the same core components as a traditional single-phase pump liquid system. It has a pump, an evaporator, a heat exchanger, and a working fluid reservoir. A key difference between pump single-phase and pump two-phase cooling is that the working fluid is close to its saturation temperature as it comes in contact with the hot device. The heat causes the working fluid to evaporate, and heat is removed through latent heat of vaporization, which, as we will see, has some very attractive benefits. To explain a little bit more about pump two-phase cooling, here is a clip from a video that's on our website and YouTube channel.
Pumped two-phase, or evaporative cooling systems, use the same basic system-level components as the pumped single-phase system. However, pumped two-phase systems typically use refrigerants as the working fluid. Through refrigerant selection and appropriate controls, the refrigerant is designed to boil as it acquires heat from the hot surface of the device. More heat can be removed through the boiling process, otherwise known as latent heat, than through sensible heat with single-phase cooling. Boiling across the entire evaporator surface offers a further advantage in that the evaporator will have a very uniform surface temperature, typically within a few degrees.
As you'll see in some of the examples, the thermal transfer power of boiling of the working fluid as it moves along the evaporator can be quite advantageous and provide benefits in system efficiency and size. To help establish and clarify a better baseline, we'll now explore a little more some of the differences between pump single and two-phase cooling. Here is a chart that compares and contrasts key attributes of pump single versus pump two-phase cooling, which are the two most common thermal management technologies used to dissipate kilowatt or higher heat loads. In terms of heat flux capability, pump two-phase has a significantly higher capability, with pump liquid systems typically in the 10 to 20 watt per centimeter squared range, and pump two-phase from 300 up to even 1,000 watts per centimeter squared. Single-phase pump liquid systems have a variety of potential working fluid selections, including water, ethylene glycol, combinations of water and ethylene glycol, and refrigerants. Pump two-phase systems, which are closed and pressurized, are usually refrigerant-based, but can be used with water, methanol, or combined water-methanol systems. A real advantage for weight and space-confined application is the significantly reduced pumping power and flow rate requirements for pump two-phase versus pump liquid systems. We'll put some numbers to that on the next page. Of course, pump liquid solutions have been around for a long time, and these solutions are reliable and well understood. Pump two-phase is an emerging technology that, while a bit more complex, is finding applications in many new areas, and modeling capabilities for these systems is improving as well. To give a clearer sense of the flow rate and pumping power differences between pump liquid and pump two-phase systems, the following comparison is provided for an avionics application. In order to dissipate 80 kilowatts of heat, a pumped liquid system using PAO as the working fluid would require a flow rate of 35 gallons per minute and approximately 5.3 kilowatts of power. A pump two-phase system using R245FA would require only 6 gallons a minute and 250 watts of power, which is an 80% reduction in flow rate requirements and a 95% reduction in power requirements compared to a pump liquid system. A significant difference for sure. Let's now turn it back to Billy for a polling question.
Thanks, Pete. It's time for our first poll question, and it should appear on your screen now. The question is, who does your company use to resolve critical thermal management issues? And your choices are A, in-house resources, B, external experts, C, a combination of both in-house and external resources, or D, not sure. So you can make your choice by selecting the appropriate button on your screen. Again, who does your company use to resolve critical thermal management issues? And as you answer that question, I'll hand the presentation back over to Pete Witt. Pete?
Thanks, Billy. Let's now take a look at some real-world examples where pump two-phase cooling is being used. We'll also look at the reasons engineers are compelled to implement pump two-phase cooling for these applications. We'll first look at a high heat flux laser cooling. In this application, the high heat fluxes must be dissipated while maintaining tight temperature limits across the diode surface. Then we'll look at a case where cooling parallel electronic boards for a pulsed DEW application must be achieved, again with stringent isothermal requirements, but also with size and weight constraints. Finally, we'll look at an example in power electronics where high operational reliability of the electronics is required. In these applications, there is concern about water leaking. In addition, the ability to remove waste heat away from an environmentally controlled room is another key thermal management concern. Laser diodes typically require lots of power, most of which results in waste heat. Vertical cavity surface-emitting lasers, for example, can have heat fluxes in excess of 500 watts per centimeter squared. Further, the heat loads must be dissipated while maintaining a uniform temperature across the evaporator surface. In many cases, pump liquid systems are not suitable for these applications. It is difficult or impossible to meet the isothermality requirements of a few degrees C, particularly when hundreds of laser diodes are involved. In these applications, a pump two-phase cooling solution is often appropriate. One can see an example of a pumped two-phase evaporator in the lower right. Flow is from left to right, and one can see the bubbles exiting the evaporator. The formation of the bubbles as the working fluid passes through the cold plate is an indication of evaporation occurring. Bubbling across the evaporator surface can provide the high heat flux dissipation and temperature uniformity required for laser diode applications. For our next example, we'll look at a heat exchanger design for directed energy weapons, DEW. These systems typically have multiple parallel electronic boards that have tight temperature uniformity requirements. Further, it is desirable to have the thermal management for these systems to be as lightweight and compact as possible. The traditional solution has been to design and build a vapor compression loop to handle the maximum heat load, even though that heat load is not always present in operation of these pulse devices. In addition to being large and bulky, these systems require additional controls, such as variable frequency drive motors to reduce the speed during off periods, and expansion valves, which have finer control. An alternative solution is to introduce a P2P loop that is coupled with a smaller vapor compression loop and a PCM heat exchanger, PCM phase change material, to store and dissipate the waste heat. This solution reduces the total overall mass, eliminates the need for some more precise controls, and improves coefficient of performance, COP, for the entire system. Here are diagrams of the single large vapor compression loop, option 1, and the improved combined pump two-phase VCL and PCM, option 2. The pump two-phase portion is highlighted in gray. In the single VCL solution, each electronic board requires an electronically controlled expansion valve, likewise requiring a variable frequency drive compressor. The pump two-phase system can use a single manifold to feed all of the boards, reducing both weight and complexity. Let's take a look at some of the advantages the pump two-phase system offers in this application. There is no need for multiple expansion valves required in the vapor compression loop. That can be handled by a single manifold. Orifices at the end of each of the cold plate provide even pressure distribution across the manifold and can be used to self-regulate the flow across each of the individual cold plates. This approach enables the transient response across the different cold plates to be more efficiently addressed. And as we have seen, it can be coupled with other thermal management systems in a space-efficient way. Finally, the temperature uniformity across these cold plates is quite good, as we'll see on the following page. Both prediction capability and actual results are impressive. We have previously stated that pump two-phase cooling systems are more complex and therefore can be more difficult to model. However, advances in modeling capability has made that less so. In the graph, we are modeling two of the cold plates from the multi-plate system described in the previous pages. The individual dots are the predicted modeling results for plate 1 and plate 2. The lines represent experimental results for those two plates. Good agreement within 1 degree C are shown between the modeled and measured results for both cold plates. Note also the excellent temperature uniformity across both of those cold plates. These results demonstrate not only the good temperature uniformity that can be achieved across the pump two-phase cooled evaporators, but also excellent modeling capability that is now available to accurately simulate these systems. Our final example of P2P applications is for cooling high-performance electronic enclosures. In many of these applications, such as data center cooling and energy delivery and other power electronics, there is a requirement for high reliability. In these applications, a potential catastrophic leak from a water cooling system must be avoided. As such, there is a requirement for a dielectric working fluid, which means refrigerants are necessary. We have already shown that many P2P applications use refrigerants. In addition, the lower required pumping power of P2P systems can reduce upfront costs of implementing these systems. That lower pumping power also enables the waste heat to be cost-effectively pumped to external locations to be dissipated. This can provide HVAC and facility savings, as the cost to maintain tight temperature limits within these environmentally controlled rooms is reduced. We have now reviewed 3 applications where P2P systems are in use. Let's now look at a couple of advances that are pushing the technology a little further. But first, we'll turn it back to Billy for a final polling question.
Thanks, Pete. Our next polling question should appear on your screen now. The question is, are you facing any thermal management issues in the next, and your choices are 0 to 6 months, 6 to 24 months, or choice C, you're not having any immediate issues. Again, make your selection by choosing the appropriate button on your screen. And as you answer that question, I'll hand the webinar back over to Pete Witt. Pete?
Thank you, Billy. In some cases, flow through parallel channels of mini-channel coolers can cause instabilities, particularly with large bubble formation that can cause severe back pressure. The bubbles can prevent flow through the channel, resulting in erratic and sometimes problematic performance. ACT, working with others, has developed a coating solution to help minimize these instabilities. The solution consists of building a microporous particle layer on the inside portion of the mini-channel structure. A concept of this can be seen on the left. The purple represents current metallic microchannel coolers, and the orange represents the microporous coating. The addition of the microporous coating adds numerous potential nucleation sites across the evaporator where bubbling can occur. This improves the likelihood of bubble formation throughout the evaporator, improving temperature uniformity. The microporous particles also absorb some of the working fluid, decreasing the probability of dry out. The advantages of this solution are listed on the lower right. It offers stable operation with minimal instabilities, good isothermal performance, low thermal resistance, and low pumping power. Above that is a sample microchannel cooler with a close-up of the microporous coating on the right. This solution can be applied to any of the applications we described previously. Let's now look at some results. Here is a summary of the test results. The test system is seen on the upper left. 3 samples were tested: a bare copper mini-channel cooler, a sintered powder microporous coated one, and an epoxied microporous coated sample. The results of the 2 coatings were similar. In the graph on the lower left, thermal resistance is plotted at different base heat fluxes. As you can see, the coated samples showed lower thermal resistances at all heat fluxes tested. The graphs on the right show test results for the uncoated sample on the top and the coated sample on the bottom. In both cases, the heat sink base temperature was taken in increments up to a maximum temperature of 75 degrees C with a heat flux of around 200 watts per centimeter squared. The temperature of the heat sink was measured regularly over an approximately 15-minute range at the highest temperature conditions. As can be seen in the graph, the temperature range for the uncoated sample was 5.8 degrees C, while the coated sample was only 1.4 degrees C. This is a clear demonstration that the microporous coating is helping improve temperature uniformity by reducing instabilities across the P2P evaporator surface. Another question frequently asked is, are P2P systems sensitive to gravity? The answer is no in properly designed systems where inlet pressure is well controlled. Here we see a lab setup with 2 parallel evaporators with flow going in opposite directions. Both can be seen in the picture on the upper left. Here, evaporator number 1 has inlet flowing coming in the bottom and coming out the top. Flow is going against gravity. Evaporator number 2 has flow coming in the top and coming out the bottom. This orientation is called gravity aided. As you can see, bubbles are exiting both evaporators, and both evaporators are at the same temperature. A close-up of evaporator number 1, seen on the right, shows the flow against gravity. Inlet flow is liquid at the bottom, and bubbles are seen exiting as the working fluid exits the evaporator at the top, indicating pump 2-phase systems can be implemented in any orientation. In the webinar today, we have reviewed pump 2-phase cooling, its advantages, operation, challenges, and some new technology being developed to address these challenges. Pump 2-phase cooling offers the potential to address increasing heat dissipation requirements up to 1,000 watts per centimeter squared by some estimates, which air and pump liquid cooling would be weight and power challenged to accomplish. Pump 2-phase systems require only a small pump and can be designed to be compact and lightweight. We have reviewed 3 specific applications where P2P systems are being implemented today. Number 1, laser diode cooling, which have very high heat flux requirements and a very tight temperature range. Number 2, DEW heat exchangers, which also have tight temperature requirements, but are also looking to minimize space and weight requirements for the thermal management system. And number 3, power electronics and data center cooling, which must maintain high reliability and therefore require the use of dielectric working fluids such as refrigerants. These applications also must maintain tight limits within an environmentally controlled room where the electronics are located. The lower pumping power requirements enable the waste heat to be transported outside the room cost-effectively, allowing HVAC and facility cost reductions. 3 different applications taking benefit of the many features of pump two-phase systems. Continuing, in addition, some new technology enhancements were demonstrated. Microporous coatings on the mini-channel heat sinks was shown to improve system stability and temperature uniformity by increasing the number of nucleation sites across the evaporator surface. It was also shown that properly designed pump two-phase cooling systems can handle multiple evaporators, even when the orientation with respect to gravity of the evaporators is different. So we anticipate that there will be additional pump two-phase cooling applications. IGBT cooling, hybrid battery packs are just a few. Now that the many advantages of pump two-phase cooling are being recognized by design engineers, we anticipate that even more applications will be found. We thank you for your attention, and we'll now turn it back to Billy for some questions.
Thanks, Pete. Now I'd like to invite Dr. William Anderson, ACT's Chief Engineer, to the line for our Q&A. So if you out there have a question, you can submit it by entering it in the box at the bottom of your screen. Bill, this question came in right away. What refrigerants do you use?
Okay. What we have used in the past is R245FA and R134, and we've also used methanol for some other applications. Basically, most liquids can be used. What you need to consider is, do you need a dielectric fluid? Do you have to worry about freezing? In this case, we can go down to very low temperatures with the refrigerants, and we need a reasonable pressure. So the refrigerant you would choose would vary with the with the operating temperature.
Bill, do you pump the liquid or the two-phase fluid?
In pump two-phase, we typically would pump the liquid, bring it up to the high pressure, flow through the evaporator. The two-phase liquid then goes to the condenser. When there is a need for a vapor compression system to get temperature lift, typically we would run the pump two-phase loop on top of the vapor compression system and keep the two things separate.
Here's another question from an attendee. In the case of two-phase cooling, is it okay if heat flux from the heat source is fluctuated?
That is not a problem at all. We've had several applications where people would like to have multiple cold plates and have some of them powered on, some of them powered off, and some of them at half power. We can design the system so that the temperature is fairly uniform for the full power and half power ones. You do have a lower operating temperature when you're not powering at all, but you very easily can switch powers between one and the other. We do have a video on our website that shows 4 sinks, and we're just turning power on and off to each of the sinks in sequence, and you do see a drop in temperature when there is no power to a given heat sink, but it comes right back up after you put power on. So in other words, fluctuation is not a problem.
Thanks. This will be our last question. How important is it to control vapor quality within the evaporator section, and how is this done?
Okay, basically the procedure we use is we want to keep the vapor quality exiting in a range below roughly 35 to 40%. When you do that, you find that your heat transfer coefficients are fairly constant with quality, so you can get away with different amounts of power for different cold plates while maintaining roughly a uniform temperature. And by roughly, I mean within a few degrees C.
All right, that'll conclude today's webcast. Again, if we did not get a chance to answer your question today, our sponsors will do their best to address them after today's presentation. So our thanks to Pete Ritt, Dr. William Anderson, and everyone out there for joining us. And just a reminder, this webcast will be available on demand at www.techbriefs.com for the next 12 months. Have a great day.